Hello, class. It's me again. Hopefully, by the time you're watching this video, you already have decent basic understanding of plastic deformation. Today, we'll continue our discussion on plasticity. In particular, we'll talk about yield surface. A little bit short recap of the lecture. What is a plastic deformation? If we draw a stress-strain curve for linear elastic material, the stress is a linear response corresponding to the strain. And once you reach a yield point, the material starts to yield. Again, I have to emphasize, if you unload the material, and if it goes back to original origin, it means there are no plastic deformation. So not all nonlinear stress-strain curve indicators of plastic deformation. But today, let's assume we're in the general context of plastic deformation. You reach a yield point, and if you unload the material, and you generate a plastic permanent deformation, and then you reload it, which can be seen in the lecture note. So today we're mostly talking about the yield surface when the material starts to yield. Recall in the lecture, we defined if a material is isotropic, the plastic behavior can be described by three principal stress. Which here we use sigma 1, sigma 2, and sigma 3 to denote the principal stress components. And the yield surface is a function which the variables are the three principal stress. So I can write the yield function as a form, or the yield surface function. The yield surface as a function of the three principal stresses. And the function closure model equal to 0. And recall another basic concept called hydrostatic stress. Which is 1/3 of the summation of the three principal stresses. And if we have already covered this in lecture, you probably know that hydrostatic stress, by its name, you can imagine you have a metal ball or any spherical shaped object, and then you put it under the ocean, deep in the water, and all the pressure are the same from all different directions, and it's a hydrostatic stress. And if we already covered this in lecture, then you know that the hydrostatic stress, it has no effect or contribution in plastic deformation. So no effect in plasticity. Or in other words, plastic deformation are caused by shear stress. So in general, because the hydrostatic stress does not contribute to the plastic deformation, the yield surface of a material should have a prismatic shape, which we'll cover later. Why is that? So I will draw a schematic to illustrate what I mean by the yield surface as a prismatic shape. So now let's say I have three principal stress components. And I can construct a base of sigma 1, sigma 2, and sigma 3. And if I define this surface that intercept all the three axes, we can call it the 1-on-1 surface. So this surface is sigma 1 plus sigma 2 plus sigma 3 equals 0. Then a yield surface of a material that's described by the three principal stress, it looks like kind of like a cylindrical shape outwards, but not exactly cylindrical. This is what I call it prismatic. So it looks roughly like this. And in the lecture note, there's a pretty good description or schematic illustrating the yield surface. And this axis is an axis where all the three principal stress components are the same. This axis is sigma 1 equals sigma 2 equals sigma 3. That's why we call the surface that's perpendicular to this axis, we call it 1-on-1 plane, and which is the surface. Okay, now this is the 3D schematic, or what does a general yield surface look like if we were to illustrate under the three principal stress component or basis. And you can project on this plane and look at what does the yield surface look like in 2D. So we can draw this in terms of sigma 1, sigma 2, sigma 3. Right, so we're just doing a 3D projection of 2D. This is sigma 1, sigma 2, sigma 3. And recall, we call this the 1-on-1 surface. Oops. And this is the axis, the pointing outwards, which is this axis where all the three principal stress components are the same. So this axis is sigma 1 equals sigma 2 equals sigma 3. And the yield surface projection, it looks roughly like this. So this is what a yield surface look like on a projection of this plane. And so there's one comment. If you were to construct a yield surface for any general material described by the three principal stress, then the important thing is we have to satisfy this curve to construct the whole yield surface, such that the yield surface is just pointing outwards towards the axis where all the three principal stress components are the same. So one needs to satisfy this curve to construct the whole yield surface. All right, so this is just the general construction or definition, if you wish, of the yield surface. And now we'll dive into a few more examples for more specific criteria we use in general engineering applications or in research. So the most classical example will be the von Mises yield criteria for condition, which is called Mises yield criteria or condition. So if you follow condition, following the lecture note. Okay, so what is Mises yield criteria? So if we have already successfully covered this part in the lecture, you probably already know what's the concept of J2 plasticity. So J2 is by definition 1/2 and the square sum of all the toric stress components. 1/2 S1 square plus S2 square plus S3 square, I think 3-dimension. And hopefully when you're watching this video, you already know how to calculate S1 and S3 after you finish the lecture. Equals K square. In the case the value that's specified by the J2. And we call this, maybe we call this equation cross. And the S1, S2, S3, we can call them the principal stresses of the dilatoric stress tensor Sij. Stress tensor Sij. Cool. And recall our previous definition. What is the definition of the hydrostatic stress? So it's defined as 1/3 the summation of all the three stress component, principal stress component. Sorry. Then you already know how to calculate S1, S2, S3 from the general stress, principal stress component minus the hydrostatic stress. So let's write it down. Let's just write it down in details, right? So what's S1? S1 should be the first principal stress component minus the hydrostatic stress. So sigma 1 minus sigma bar, right? Same for S2, sigma 2 minus sigma bar. And S3 equals, whoops, it's poor space management, I guess. Let's see, okay. So let's say this is a definition of the three deviatoric principal stress, right? So we use this formula, we substitute back into this equation, then my favorite term that I like to use in public session and lectures, we do some algebra, right? And for efficiency to deliver the main message, I'm going to skip the algebra. So what is the conclusion by using the algebra? So k squared, the value we defined here, by construction or by definition equals to J2, which is 1/2. The three principal deviatoric stress component. So just plug in this and do the algebra. Sigma 1 minus sigma bar square plus blah blah blah. Just do it back here. Then after the algebra, what do you get? You get this 1/6. And algebra is in the lecture note, so please refer to the lecture note if you want to do the algebra and check it yourself, right? Sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. All right, so this is k squared. So what is this? What does the yield surface look like? Since it's a video, I cannot give you a quiz or pick a student to answer the question. So I'm going to tell you what does it look like, right? It looks like a circle. So if we were to draw this, the principal stress projection, let's say sigma 1, sigma 2, and sigma 3. The yield surface that projected on this plane, it looks like this. So this is what we call the yield surface. All right, and again, just to re-emphasize my point, so this axis pointing upwards, because this plane we call the 1-1 plane. So this axis is where sigma 1 equals sigma 2 equals sigma 3. All right, but it looks like a circle. And I'm not sure about you guys, but if I were to, I'm having to watching this video and I look at this, okay, you do some algebra, you have 1/6 sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 plus blah blah blah. How do you intuitively just make the conclusion that this looks like a circle? Actually, this conclusion is what I just directly give it to you guys, and now I'm going to prove it, right? So why does this formula, this complicated formula, unless you have genius mathematical intuition and you can imagine a circle, it'll be very hard, at least for me, it'll be very hard for me to directly see a circle out of this algebra. So now I'm going to prove it to you guys why does this equation end up to be a circular yield surface on the 1-1 plane projection, principal plane projection. And the thing is, I'm not going to prove it mathematically. I'm going to prove it geometrically, right? So I'm going to give you a geometric proof. So how do I prove it geometrically? Then I first wipe out the general definition and I use this part of whiteboard. So we start with this plane projection. Now let's draw this plane right here. Right, I said this is the 1-1, the projection plane, right? It has a normal axis pointing upward, which is this 1, 1, 1. All right, cool. And the plane has three, so in the projected direction, the plane has three. Go this way, three axes. Let's call them S1, S2, and S3. And as we know, S1, S2, S3 are the three principal stress components minus the hydrostatic stress. If this is the origin, we have the three principal derivative stress component, and the three principal stress components on the schematic, it looks like this. Is actually a point outwards the plane. So again, this is this is S2, this is sigma 1, sigma 2, and sigma 3. Okay, nice. And let's say if we were to draw this, this is their second projection, their relationship, like this. All right. And the three principal stress components, sigma 1, sigma 2, sigma 3, they signify as three axes. But as we recall, this is 1, 1, 1, right? So how do we write sigma 1, sigma 2, sigma 3? I'm just directly give you the conclusion with 1, 0, 0, 0, 1, 0, and 0, 0, 1 there orthogonal. So for sigma 1 is by construction is 1, 0, 0. For sigma 2 is 0, 1, 0. For sigma 3 is 0, 0, 1. Cool. And there's a term, if you go to lecture note, there's a specific definition for this plane. We call this plane called the pi plane. And we'll be using that a lot. And one more comment, which you guys probably already know the answer is, what is the 1, 1 axis again? It's the axis where all the three principal stress components are the same. So sigma 1 equals sigma 2 equals sigma 3. In this plane, if this is the origin of the coordinate system, then again, this plane signifies sigma 1 plus sigma 2 plus sigma 3 equals 0. And from the definition of S1, S2, S3, the three principal deviatoric stress component, my favorite term again, we're going to do some algebra, which I'm going to skip. So from some algebra, right? What we get? We get S1, S2, and S3. It can be written in the form of the three principal stress components, sigma 1, sigma 2, sigma 3, which I'm going to give you the conclusion. 2 sigma 1 minus sigma 2 minus sigma 3 divided by 3 minus sigma 1 plus 2 sigma 2 minus sigma 3 divided by 3 and minus sigma 1 minus sigma 2 plus 2 sigma 3 divided by 3. Okay, so this is the 3D schematic of the axis, the basis, or what it generally look like. Now I'm gonna imagine I have I'm gonna do a top-down view, right? Do the projection. What does this projection look like? Say I have three principal deviatoric stress components. So I have S1, S2, and S3. And this is the origin. And now here's a trick. I'm going to define a new axis. Because when you do the projection on this plane, let's say in the general 2D case, usually when we build a Cartesian coordinate system, you have X and Y, and the two axes are perpendicular to each other. So now, because remember, now I'm actually doing, just to remind you, if in case you forget, now I'm trying to do a geometric proof, right? So when I'm doing geometric proof, we want to go to something that we are familiar with, which is try to sort of construct a Cartesian coordinate system where you have orthogonal axes. So I'm going to define a new axis that's pointing towards a traditional x direction. So that's such that S2 is pointing towards the, in a general sense, y direction, if that helps. So I'm going to call this S1 tilde. And again, I just want to emphasize that, this is by construction, or we construct this. All right. And to mathematically represent this axis, we have out of plane, we have 1, 0, 0, we have 0, 1, 0, 0, 0, 1, and this is 1, 1, 1. So in a general formulation, the mathematical formulation for this axis for S1 tilde is written as 1, 0, minus 1, or 1 bar. 1 bar is basically minus 1. Yeah, so if this is 1, 0, 0, then minus 1 is pointing towards the opposite direction. And just one more thing. So the 1, 0, 1 bar, this axis is not exactly S1 tilde. Is you have to scale S1 tilde by square root 3. So S1 tilde. And so now I call this, but we're still doing the one Mises material. So what is S1 tilde mathematically? How do we write that? S1 tilde can be written as a function of sigma 1 and sigma 3. So it's actually sigma 1 minus sigma 3 divided by square root 3, which you substitute the equation I just wiped out, you substitute the hydrostatic, and the hydrostatic stress can be canceled out. But this turns out to be S1 minus S3 square root. Okay. And we define this equation as equation star. And this is a pure geometric construction of S1 tilde based on S1, S3. So from this equation, we can further derive the correlation between S1 and S2, and also S3 and S2, because we know there's a correlation between S1, S2, and 3. And then we just design S1 tilde. So then we can, through S1 tilde, we can build up the connection or construction, finding the correlation between S1 and S2 and S1 tilde. So, from equation star, we can get S1 equals half square root 3 S1 tilde minus half S2, and also S3 minus half square root 3 S1 tilde minus 1/2 S2. All right, so we're still in the middle algebra. Recall this is the definition of the whole Mises stress criteria, which is the J2 equals K squared. So now we're gonna substitute equation star and the equation that we derive from the equation star, because we already know the correlation between S1 and S1 tilde, or S2 and S1 tilde, S3 and S1 tilde. So we're gonna plug this back into equation cross. So gonna substitute this back to equation cross. So what do we get? We have K squared equals J2 equals I'm just using the definition equation we just wrote down, right? 1/2 S1 squared plus S2 squared plus S3 squared. So far, it's everything the same, no difference. Doing the algebra, what do we have? 3/4 S1 tilde squared plus S2 squared. Now this thing is becoming interesting, right? So if you have a good mathematical instinct, when you see this equation, you probably have a sense, okay, this looks, basically it's telling us this is a circle, but we can further move a step forward, right? So what's the equation of a circle, or how do we move this, make some connection with the actual equation of a circle? Basically it's x minus some position, the origin, right? If the origin is at the origin of the coordinate system 0, 0, then is x squared plus y squared equals r squared. So we can reconstruct this equation into S1 tilde square plus S2 square equals, we substitute this back and do the algebra, right? There's k square, and then the 3/4, then it becomes 2 square root of 3 k squared, right? And further, from the lecture, you probably already know the correlation between k and yield stress. Just in case, if I didn't define a symbol, the yield stress is sigma y. So and you substitute k and sigma y using the square root of 3 correlation, then you have 2/3 yield stress squared. So this is literally the equation of a circle that using pure geometric concept, we kind of prove that the von Mises stress yield surface is a circle, right? Okay, so I hope now this clarifies or clear your understanding. And one more comment. So we finished the geometric proof and the von Mises yield criteria is 2/√3 k equals, or k is by constructed by definition, the square root of J2 is 2/3 yield stress on the pi plane, which is the plane we just defined, the 1, 1, on pi plane. This is an important conclusion we obtain from just by doing mathematical geometric analysis. And we can then define the yield surface much more accurately or precisely. On the pi plane, the 3 axis that's being projected on the plane is the 3 principal deviatoric stress component, which is S1, S2, and S3. So we can plot or sketch a schematic. We have S1, S2, and S3. You have a circle. And this axis is pointing outwards is a 1, 1, 1 axis, where as I have repeated like 100 times, where all the 3 principal stress components are the same. And on the surface, because this is the yield surface, so all the points that's being light on the surface satisfy 2/√3 k equals 2/3 yield stress, which is the von Mises yield criteria. And then the radius is literally 2/√3 k. Okay, nice. So this is the general construction of the von Mises yield criteria in 3D. And having taken this class for 5-6 weeks now, you probably already know to solve problems, we like to solve problems in 2D. 3D is good for research, right? But we want to try to construct simplification in 2D such that we can derive an analytical solution. So what's the Mises yield criteria in 2D? I'm gonna briefly derive the condition under plane stress. So what is the Mises yield criteria under plane stress? All right, I got a Y geometric two-part. And if you recall, how do we define plane stress? Which is sigma 3 equals 0. The third principal stress component 0, because there's no stress in the z direction. And correspondingly, third principal stress also goes to 0. And we already know this is a definition or by construction. We construct, this is how Mises criteria is being defined. So we just literally substitute the equation to J2, right? So what is J2 here? J2, by skipping the algebra, we directly use the conclusion 1/6 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. And using my favorite term, in some algebra, what we have, eventually we end up with, because we don't have sigma 3, right? We end up with 1/3 sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square equals k square. Cool. And what can we further get from this equation? We further obtain the sigma 1 square minus sigma 1, sigma 2 plus sigma 2 square equals square root 3k square, which is the yield stress square. Okay. And the shape of the yield surface on the projection of the two principal stress, because there's no such thing of the third principal stress on the plane stress. So if you plot it under sigma 1 and sigma 2, if you observe this equation, what would be your intuition? I don't know. If your intuition is probably looks like an ellipse, then congratulations, you have the correct intuition. So it should roughly looks like this. So you have sigma 1, sigma 2. This is the origin, right? This equation corresponding to shape that looks like this. And this is the yield stress, sigma y. The intersection between the yield surface shape and the principal stress axis should be sigma y. So this is what we call the shape of yield surface in 2D under plane stress or something. And just a few more comments of this yield surface, such that you have a deeper understanding of this yield surface, right? So what we call, a few special points. First thing is under pure tension, sigma 1 under pure tension scenario, sigma 1 is a yield stress, and sigma 2 is 0. You're stretching in the one direction. Right? And under pure shear, sigma 1 equals k by construction, the square root J2. And sigma 2 equals minus k. Third one will be much more interesting. So for material under biaxial tension, you're both pulling on the two axes simultaneously. both sigma 1 and sigma 2 equals the yield stress. Hope you can see that part clearly. Nice. So we finish the Mises yield criteria. We first derive it based on the definition. We first derive it in 3D, and then we sketch and what does it look like in 3D on the principal one plane, the pi plane projection. It looks like a circle, and then we derive what does the Mises yield criteria look like in 2D under plane stress assumption. And if you're interested, welcome to do another exercise deriving yourself plane strain and applying different loading conditions and see what's sigma 1, sigma 2 under plane stress and all that. You are very welcome to also ask me questions after class about this too. But we have finished Mises yield criteria. Now we're going to go to another famous yield criteria called Tresca yield criteria or Tresca yield condition. And I'm going to wipe out a thing about Mises. So I'm just gonna mark that, okay, we finished this, right? See if I have a better marker. Oh, nice. Okay, this one's good. All right. Boy. So I'm gonna start with Tresca yield condition. So what's by definition? What is Tresca yield condition? By construction, by definition, Tresca is defined as the absolute difference between any two principal deviatoric stress components equals to a constant, which we define as 2kt, where T signifies Tresca. So S1 minus S2 value equals 2kt. S2 minus S3 equals 2kt. And S3 minus S1 equals 2kt. And well, I already erased that, but if you still recall, I define a thing called S1 tilde first to illustrate what does the Mises yield stress look like on the pi plane. And then we use S1 tilde to explain it looks like a circle. So we're gonna still use S1 tilde here in the Tresca period. So we can write this whole condition, or write in terms of S1 tilde and S2. Again, my favorite term. We're gonna skip the algebra. Let's do some algebra. The absolute value, square root 3 over 2 S1 tilde minus 2 S2 equals 2kt. Now because it's kind of like doing a geometric projection or operation such that you have 3 axes, and then now you fine tune, and now you only operate on 2 axes. 2 degrees of freedom using 2 variables. Now you only have S1 tilde and S2. And this is the same, square root 3 over 2, S1 tilde plus 3 over 2 S2 tilde. Absolute value equals 2kt. And the third formula equation will be square root 3 S1 tilde equals 2kt. So this is the mathematical definition of the Tresca yield criteria. And this forms, this whole mathematical form, if you look at it in terms of S1 tilde and S2, it conform, or it has a shape of hexagon with a side length of 4 over 3 kt. So this form, in terms of S1 tilde S2, is a hexagon of side length. Oops. Four over 3 kt equals 2 over 3 yield stress. And when I just say hexagon, it probably, for some of you it might click, but for some of you might still wonder what does it look like. So I'm gonna sketch it, schematic. So this is S2, right? Recall S1 is perpendicular to X2, sorry, S1 tilde. And I must still draw S1 and S3. Oops. Geez. So what does the Tresca yield surface look like? It looks like this, and then I can project it, elongate in the opposite direction. Looks like this, and then S2 looks like this. This. Okay. That's a little bit weird shaped hexagon, but I'll take it. Okay, it looks like this. And the intersection of the two axes would be 2 over square root 3 kt, right? And this will be the Tresca yield surface look like according to this definition of mathematical construction. And this side length is 4 over 3 kt, 3 kt. Okay, and since I didn't wipe out the von Mises yield condition, I still preserve the text. If this is a lecture, you would naturally expect me to ask a question: what's the connection between the Tresca and von Mises? I will not literally ask you to do the algebra because it will be too complicated. But if I were to ask you to make a educated guess, what will be your intuition? The conclusion is the Tresca yield surface, or the yield condition, is inscribed by the circle of the von Mises yield criteria. So I'm going to write it down, and then I'm going to sketch it to explain what do I mean by that, right? So the conclusion is the Tresca yield condition is inscribed by von Mises. So when I write von Mises circle, you probably know what I mean, right? It's the yield surface projection on the pi plane. And I'm gonna sketch the schematic for that. So see, on the pi plane, I have 3 axes: S1, S2, and S3. And I simultaneously gonna draw S1 tilde. Elongate 3 axes. What does a von Mises yield criteria look like? Because you recall, or previous part of this video, it looks like a circle, circular shaped yield surface. I can draw this nice, beautiful circle. Look at that. Wow. Okay. And what is the Tresca condition or yield criteria look like? Because I already tell you it's inscribed by the circle. So on this projection plane, it will literally look like this. And this circle is the Mises yield criteria or yield circle. This will be Tresca yield, or we call it yield surface, right? Yield surface pointing towards the one axis. And so this is in the general case. What about in 2D? What about the plane stress? Because we literally just derive what Mises yield surface look like in 2D, right? So in 2D, the conclusion remains the same. I brought here. Hope you guys can see it. I have space here. Okay. So if this is sigma 1 and sigma 2, in 2D, it would look like this. So this is the Tresca yield surface, and this is they have the same intersection of the axis. Just to clarify, this is the von Mises, and this is the yield stress sigma y. Is minus sigma y, right? And so this would be the von Mises. And this, the internal one, that is being prescribed, the Tresca. Okay, so we have geometrically explained both the von Mises and Tresca yield surface, and show you what does it look like intuitively, either in 3D or on the projected pipeline. And now we're going to do a little bit deeper, which we actually entered the research part of plasticity, which is a very popular hot topic in solid mechanics, which is the flow rule. And I'm gonna wipe all the equation I have for Mises and Tresca. So I'm going to use an example. It's probably the simplest example we can have, which is there's no string hardening. We use a perfectly plastic material. So what is the flow rule for a perfectly plastic material? And I would assume, or at least I hope, by the time you're watching this video, you already finished the lecture, and I hope it is being covered. What does a perfect plastic look like? Stress and strain. Once you reach the yield point, and stress remains the same. There's no strain hardening or strain softening. And also, I would assume you already know the basic equation of plasticity, at least from lecture note chapter or handout number 13. Now I'm doing 14, right? So the elastic response, according to the basic fundamental equation of plasticity, the elastic response would be the shear part of the elastic strain, which we use little e to denote. Eij, elastic, it's the shear, right? You already know, so I don't need to write down. Equals 1/2 mu. Mu is the shear modulus and deviatoric stress. And if we were to make an increment or the direction of the elastic deviatoric elastic strain, then DEIJEL, the direction is 1/2 mu DSIG. This is just linear algebra. Sorry. derivative. Or the I was supposed to say calculus. Anyway, a plastic response would be so plastic. Here is a strain rate. So we're talking about flow rule, right? This is rate. It's 1/2 mu, and I hope we already know what's the rate, right? Time derivative. Lambda tilde ij is the parameter that is elaborate in the lecture note, and hopefully be delivered in the lecture. We calculate d epsilon ij plastic is Sij over 2 mu lambda tilde dt. And by combining the plastic and elastic increment, so then if we move, if we make a step forward, and the total meatoric strain increment would be dEij equals the elastic part plus the plastic part. dEij elastic plus d epsilon ij plastic. And you literally just substitute the equation to the algebra, then you end up with dsij, the meatoric stress component, over 2 mu plus Sij over 2 mu, and then just plug in this formula dt, because you're doing strain rate. Here comes the most, I would say, interesting or challenging part of this video, which I hope to use this to wrap up this video. How would you interpret the classic flow process, at least under the context of a perfectly plastic material, geometrically? Because, you know, for the first half of this video, we've been doing a lot of geometric interpretation under the principal stress axes or space. How do you interpret, well, Mises yield criteria and Tresca yield criteria? So how would you interpret, geometrically interpret the plastic deformation once you reach the yield point? I'll try my best to deliver this. So now let's say you have an origin, right? And then you have a stress path to load this material. And now let's say this is, you know, a yield surface. Okay, so this is the yield surface. And now you're gonna start to load this material by incrementally adding stress. And now let's say this stress passes towards this, you know, on some space, in some Euclidean space. Then so your stress pass. And before you're reaching the yield surface, you're in the elastic regime, where if you apply a stress, the corresponding strain path should be proportional, because it's elastic response or elastic deformation. So it should be proportional to the applied stress, right? So, you know, if this stress is following this stress path, I'm loading according to this path, then, you know, these are different stress projection, and this is the point where the material yield, right? And we'll call this deviatoric stress path, to be precise. And before I reach the yield point, in this regime, I'm still in the elastic regime, so they're proportional. So given this stress, the corresponding strain, you know, should look like this. which is literally elongated until you reach the yield point. So the moment you reach the yield point, before you go beyond the yield point, it is still proportional. So if this is the deviatoric stress path, we can call this the deviatoric strain path. And based on our calculus knowledge, we know this, if the stress follow path and those are the stress components, then you can calculate the derivative and you know what's the direction of dsj, so those are sj, right? So the dsj, say it follows this direction. This is dsj, right? So accordingly, those stress components, they have their corresponding dsj, et cetera, et cetera. Okay. Now let's say this is where yield happens. So when the stress reaches the yield point, the strain path no longer proportional to the stress path. And it will start to change, right? So let's say it changes to this path, because now you are entering, there's no string hardening, so the yield surface stays as it is, right? I mean, if there's string hardening, the yield surface can potentially expand, and there's string softening and shrink. You know, they're very complicated mechanism, but because we're talking about a perfectly plastic material, the yield surface remains as it is. And for any strain path, let's say if the strain follows this path, and at this particular point, you can calculate your deviatoric strain according to the fundamental equation of plasticity. So let's say here, the EIJ, well, the algebra by definition, the change or the direction of EIJ, if I were to take a further step, right? Take a further step. DEIJ, following the equation we just derived, is the elastic part of the deviatoric strain plus the plastic part, epsilon ij, plastic. And by construction, this formula we know is a vector operation, right? So if this pointing to DEIJ, then this can be decomposed to this as DEIJ elastic, and this will be DEIJ plastic, right? So DEIJ elastic is DSIJ, following the definition, making a step change of the deviatoric stress divided by the shear modulus. And this part would be the epsilon ij plastic, which is Sij. And since we start with the plastic strain rate, right? So it's Sij over 2 mu shear modulus lambda dt, which we're making time increment. So this is this is vector algebra. All right, cool. And just one thing that we always stay in mind, EIJ before you reach the yield point in the elastic part, is because you're having in the elastic regime following elastic response. So it's 1 over 2 mu shear modulus correlate with the deviatoric stress component. There's EIJ and SIJ correlation in the elastic regime, and once you reach the yield point, the strain propagate or step forward according to the fundamental equation of plasticity. Geometrically, you would imagine the strain propagate forward towards this in a discretized sense. And I know this is kind of abstract. I agree, but this is something that if you have this mental image in mind, and then when you write down the algebra, will be very helpful because your mind can kind of imagine what happens once you reach the yield point in abstract space mathematically what is happening, and there's a mathematical correlation with this image. One comment: the applied stress dsij, it only contributes to the elastic string. So they are actually in this space is parallel. dsij and deij elastic. And according to this equation, Sij and deij plastic is parallel, right? They're in the same direction because we start by specifying the plastic strain rate, as I repeated probably 100 times, right? So this is Sij, the direction of Sij. Then according to this equation, d epsilon ij plastic propagation of the plastic deformation is parallel. So these are parallel. Okay, nice. Just one final thing. We'll have a more detailed geometric interpretation. So when you apply any stress following this levatoric stress path, before you reach the yield point or reach the yield surface, before Sij reaches the yield surface, you are in the elastic regime, in which Eij, the deviatoric strain, is parallel to Sij, right? Because it's pure elastic deformation. And correspondingly, DEIJ is also parallel with DSIJ, the increment. But after you reaches the yield condition, EIJ is no longer parallel with Sij, right? Because there will be plastic strain that is being generated, right? So it's no longer parallel. And similarly, DEIJ and DSIJ are no longer parallel with each other. But instead, what's actually happening is, for the fundamental equation of plasticity, DEIJ, it equals DEIJ elastic, the elastic portion of the deviatoric strain, plus you can write epsilon or the E because again the hydrostatic stress does not contribute to plastic deformation, right? So you can also write it E, right? EIJ plastic. If you follow this equation, both elastic and plastic strain contribute to the overall incremental deviatoric strain, then the elastic strain is parallel to DSJS. I just erased it, but according to the schematic that I just sketched, and the plastic strain is proportional to the deviatoric stress, not the stress increment anymore. So Sij. Again, this video serves as a guidance for help you to read the lecture note yourself. If I made any mistake or contradict with the lecture note, please stick with the lecture note. It's probably I made a mistake or error during the video, and yeah, feel free to ask me questions about this. around office hours, problem session, or lectures. And I hope this video can help you understand the handout, the lecture note much better, and have a more physical, intuitive understanding of plasticity, yield surface, and beyond.